So in this scenario, we are having a siren of a stationary train, which emits sound waves of a constant frequency of 780 hertz. Then a person in a car with a detector accelerates constantly from rest at point X towards the train, then take the speed of the sound in the air as 240. So we're having a train which is producing or which is emitting sound waves with a frequency of 780 hertz. So that should be the frequency of the source, which is equal to 780 hertz. Then this source now is stationary. So the velocity of the source is 0 meters per second. Then now a person in a car with a detector. So that means this person is a listener. So the velocity of the listener and the frequency of the listener. So this detector now accelerates constantly from rest. So that means the initial velocity of the detector is 0. Then the final velocity we don't know. Then take the speed, so we don't know these quantities. Then take the speed of the sound in the air as 340. Then name the phenomenon that was observed by the listener. So this phenomenon is Doppler effect. Doppler effect is when there is an apparent change between the frequency detected and the one that was emitted, so provided the source or the listener, either of them is moving and the other one is stationary. All right, so this should be Doppler effect because the detector is moving but the source is stationary. So this phenomenon is Doppler effect. Then 6.2. Now we need to calculate the wavelength of the emitted sound waves. So we know velocity is equal to frequency times wavelength. So we need to calculate the wavelength of the sound waves, and we know the speed of the sound is 340. Then the frequency of the sound is 780. Then the wavelength is the one that we want. Okay. Then we're going to divide by 780. Divide by 780. Then the wavelength will be equal to 340 over 780, which is equal to 0.44 meters. So that's the wavelength of the emitted sound waves, because the frequency that was emitted was 780 and the speed is 340 in the air. Then the next question, 6.3. Now explain why the observed frequency is higher than the emitted frequency. Okay, so as the car is moving or is approaching the stationary train or the source of the sound, so the frequency of the sound is increasing. Frequency is increasing. Or why the frequency is higher than the emitted frequency, because the wavelength decreases. So what is happening here is that as the car is moving towards the train, so the sound waves are going to collide with the car. So as a result, the wavelength is decreasing, which result in an increase in frequency. So more wave fronts will reach the ear of the detector, or the detector itself, the detecting machine. All right. Then 6.4. Then in 6.4, at point Y, so the car was accelerating from rest at X, then it undergone a displacement of 83.11 meters. Then at point Y, the person in the car measures an observed frequency of 850. So now we are given the frequency, which was, or the frequency of the listener, which we didn't know initially. All right, it is 850 hertz, which is greater than the frequency of the source. Now we need to calculate the speed of the car at point Y. Okay, so now we recall the formula, the Doppler effect formula. So frequency of the listener is equal to velocity of the sound plus or minus the velocity of the listener over v, which is the speed of the sound in air, plus or minus the velocity of the source times the frequency of the source. Okay, now the velocity, the frequency of the listener is given to be 850. Okay, so we're going to substitute in this equation 850. But then the speed of the sound in the air is 340 over 340. Okay, then now we need to choose between positive and negative. All right. Okay, so how determine if we're adding or subtracting in the numerator? Okay, we know that. Okay, let's first put the frequency of the source. So the frequency of the source was 780 over 1. Okay, then we know that initially the frequency was 780. Then it increased to be 850. So that means the numerator should increase, because this is the numerator. We have 1 there. So the numerator increased. So we must add in the numerator. So we're going to have VL. Then if the numerator is increasing, automatically we're subtracting in the denominator. So if, for instance, here we had maybe 650. So we're going to 650 is less than 780. Then we're going to subtract here. Then we're going to add here. Now that we're having a number which is greater than the frequency of the source, so we're going to add here. Then we're going to subtract here. Okay. Now the velocity of the source, our train is stationary, so it is 0. Then the velocity of the listener is the one that we want. Okay, now it's the matter of simplification. Okay, so now we're having 340 plus the velocity of the listener times 780 all over 340 minus 0 times 1, which is 300. and 40. Then on the left hand side, I have 850 over 1. All right. Then we need to cross multiply. Then we're going to have 850 times 340, which is equal to 340 times 780. Then plus 780 times the velocity of the listener. So we recall our distributive law. All right, from mathematics. Okay, so now we need, so now we can transpose this number over here to the other side of the equation. So we're going to have 850 times 340 minus 340 times 780, which is equal to 780 times the velocity of the listener. Then we can divide by 780 both sides. And then the velocity of the listener will be equal to, so you just type that in the calculator, 850 times 340 minus 340 times 780 over 780. This should be equal to 30.51 meters per second. So that is the velocity of the listener, or the velocity of the car at point Y, because the listener is within the car. So both the car and the listener travels at the same velocity. All right. So that's the final velocity, because initially the car was at rest at X. Okay, so let's draw this scenario. So we have point X, we have point Y. So the speed of the car at point X is 0 meters per second. Then the speed of the car at Y, it's 30.51 meters per second. Okay, then the displacement that was undergone by the car, so it was delta X is equal to 83.11 meters. So that's the displacement. Okay, so now we need to quantify the acceleration of the car. So how are we going to calculate this acceleration? So we recall our equations of motion. So we have this equation of motion. You can check at the back of your formula sheet. So Vf squared is equal to Vi squared plus 2a delta x, where a is the acceleration and delta x is the displacement. Vf and Vi are the final velocity and initial velocity respectively. So we know the final velocity is that one over there. So we're going to have, okay, before we even substitute, let's just manipulate this thing. Then, so we're going to have Vf squared. Then we're going to transpose this guy. So we're going to minus Vi squared. This will be equal to 2a delta x. So we want acceleration, so we can divide by 2 times delta x both sides. 2 times delta x. Okay, then okay, we're going to get our acceleration being equal to V final squared minus V initial squared over 2 times delta x. Okay, now let's substitute our values. Then our V final is 30.51. 30.51 all squared. Our initial velocity is 0 because the car started at rest. Then 2 times the displacement, it's 83.11. 83.11. So the acceleration of the car will be 30.51 squared minus 0 squared. So 0 squared is 0 divided by 2, 83.11. So the acceleration should be equal to 5.6 meters per second squared to the right. To the right. Yeah, that's it.